Hi, my name's John. I'll share my screen right. Oh, I think somebody else is sharing. I believe Teresa's sharing. So Teresa, do you want to start off and give an overview?
Sure, just very quick. High frequency radars, they're land-based radar systems that measure ocean surface currents, coastal currents. And there is one particular problem that we have sometimes with our quality control. So that's the focus of this project. So these are at a very raw level. There's Doppler spectra data. That's where we're getting the velocities from. And the thing that's a problem here is this echo. It's from the ionospheric layer. But what happens is, this is a map from a radar station. What happens is when you get that band of high velocities, it can get into your station data, your map of these surface current velocities. When you take all the station data together and you make a gridded surface current velocity map, that can end up as kind of this arc of, artifacts from the ionosphere. These are not real surface current velocities. So we have some tools to get rid of this, but they don't work all the time. So that's why that's the motivation for this project. I will let John, who did all the work, mostly for this project, continue with the presentation.
All right, thank you. I'll share my screen really quickly just to kind of, okay. So the way that I started trying to solve this problem was by first looking at the way that a lot of the processing is currently being done. So things are currently really being done in MATLAB, which is something that's not, it's used a lot in academia, it's used a lot in industry, but it's not always used in like sort of open source hackathon type community because it's licensed. So as a software developer, the first task was to try and create a Python package that would be able to do at least some of the same things that some of the current processing in MATLAB is capable of doing. So I put together a Python package that is more or less at the core a means to read and process data, high frequency radar data, as it's typically stored straight from the source. So I went in and I did some digging and I found the binary format for all the data. It's kind of long and kind of involved. And I built out a parser for it. So I built out a representation of the file in Python, and I was able to basically create a really nice looking interface that allows you as a researcher to simply import something, and very similar semantics to how you would load JSON or some other file format YAML in Python. You can load an object that represents a cross-spectrum file. The cross-spectrum file format has a pretty long header that has a lot of metadata related to the radio, and it also has the frequency spectrum, range-dependent frequency spectrum from 3 separate antenna, as well as some what are known as cross spectra, which basically represent interference patterns between different antenna. So there's different types of processing that you can perform via the notion of a processor. So
I have 4 minutes.
I have 4 minutes left.
Nope.
Sorry, I'm at 4 minutes?
Yes.
All right, well, I'll briefly finish up then and I'll explain. So we have signal processor, which essentially allows you to do a lot of custom pre-processing, compute gains, etc. And what this allows you to do is to basically have a really nice interface for working with the data in Python. Now, I'll stop share quick and share a different screen to kind of demonstrate some of the filtering results. So excuse me. So first thing I'll show is the result of some of the filtering using PCA. So what I was able to do is I was able to take some data, train a PCA module to try and reduce the dimensionality of the problem, and I thought I'd be able to reduce some noise components. So the top image has this very broadband scattering noise, and the bottom image is basically taking a certain number of the components that should represent the highest, that account for the highest variance in the data. This turned out to not be super effective just because a lot of those components seem to be coupled as far as PCA is concerned. So the next thing I tried was basically the use of a
John, we are not seeing anything. Sorry for interrupting, but you're also over time. So do you want to try show one figure and just do that one?
Sure. Can you see this?
Yes. All right. Cool.
Okay.
I'll give you time for this one. Only.
I'll just explain quickly. It's a match filter. Basically, I use a thresholding method where I can calculate the dBm of the signal compared to some reference, and then I can use the threshold to develop a smoothed out match filter. What that's able to do is it's able to multiply in the frequency domain the actual signal. And what this is able to do is able to completely get rid of things that are on the side. The limitations are that calculating the gain is not very robust and has to be done in a somewhat sophisticated way, which is something I look forward to developing. But essentially what you're able to do is you're able to apply an FIR filter in the frequency domain, which is more or less equivalent to convolution with a set of signals centered around the scattering distribution of waves moving towards you and waves moving away from you. So the hope is to develop this out further and add it by expanding the package that I developed, and hopefully be able to, if effective, integrate with some radar systems that have this issue. Yeah, so sorry I went over, but that's it. Anyone have any questions or anything?
Sorry, we don't have time for that, but Felipe wants to say something. You can unmute yourself.
It's very briefly because we don't have time. So because this is a package of general interest, and I know a lot of people will want this, ping me and I'll help you find a home for it. Take care of CI testing and etc. and all the boilerplate. Because if it lives here on the OceanHackWeek repository, it may fall under the radar. Bad pun, sorry. So anyway, ping me and we'll talk.
All right, thank you very much.